All right. Okay, so we just looked at the variational form, and what we said is that we are still in an infinite dimensional space. So what exactly that means? So, well, if we take a look at what the energy space is, it's infinitely dimensional. Basically, that means that you can write our U, or displacement field, as a sum of functions from 1 to infinity. In fact, in many books on finite element analysis, there are proofs that you can show that the strong form of the boundary value problem and the weak or variational form are equivalent statements of the problem, just because of this fact that you are still working in an infinite dimensional space. There are you can go from one to the other and vice versa, and then you show that both are equivalent problems, or the two forms are equivalent. But it is just because, one more time I'm going to say, it's just because we're still working in an infinite dimensional space. Yeah? So what I wrote here, so these guys are what we call basis functions. Of course, those are the basis functions that span. You're also going to see those span that energy space. And these ones are the so-called degrees of freedom. Yeah? Sorry? Alpha I. Those are the degrees of freedom. Yeah, the first one is a phi. Sorry for my handwriting. I'm not good at Greek. Anyways. But we said that we are not interested in working in an infinite dimensional space because, to start with, we cannot actually solve any problem that is infinite dimensional in a computer. We have finite amount of memory. And so we are going to relax that restriction, and I'm going to work now in a finite dimensional space, or a subspace of that infinite dimensional space that we call the energy space, right? And so we relax this requirement. And look for a solution in a finite dimensional space. And well, how do you say that? Well, if E of omega is our infinite dimensional space, we normally use a superscript h to denote that we are already in a finite dimensional space, and h is normally in finite element terminology related to the mesh size, so h is normally the size of the finite elements that you use, right? That's also why it's called the h version of the finite element method. Okay, and of course this is going to be a subspace of E of h. Yeah. Now, the moment we do this and we go from infinite dimensions to a finite number of dimensions, then something happens, because most likely we're not going to get the exact solution, right? And therefore there is going to be an error. Now, are we fine with that error? To having an error, are we fine with it?
Yeah.
Why?
As long as it's small enough.
Ah, that's key. As long as it's small enough is the key answer here. So we're fine with that error, but as long as it's small enough. The question is, how do we quantify that it's small enough? Huh? How do we quantify? How do we know when we solve for a problem that the error is small enough? In fact, most people solve for a problem using a finite element package, and they have absolutely no idea what the error is. Right? And this is This is why you are taking this course, because you're going to be able to quantify that error, right? And you're going to see, well, is the error small enough? Well, it is. Why? Well, because I have an estimate of my exact strain energy. If I have that, right, I can see how far I am from that strain energy, and then I can quantify, and I'm okay with this level of error, right? And that is what this course is teaching you. Yeah.
It's still an estimate, so
it's still an estimate, but it's a very good estimate, and you will see when you're solving the project. In fact, normally when we do a posteriori error analysis, you use basically three discretizations to estimate the value of the strain energy. So in some way you are solving a nonlinear equation, and by doing so you are basically extrapolating to see what is the actual value of the strain energy, right? And you will find when you do the project that is actually very, very close to the exact value. And well, let me ask you, it's still an estimate, right? So how do I know whether this is a good estimate? What will you do? Yeah?
you check how big the error is relative to your outcome, or also check the dependency of your error on the mesh size or time step used as well.
Yes, we are going to do that, but that's still not the question. The question is, well, if I compute an estimate of the strain energy, it's still an estimate. So how do I know if that is a good enough estimate? So what will you do? Say you use three meshes, different meshes, and you obtain an estimate. What will you do next to know whether that estimate makes some sense, if it is good enough? Sorry, no, you don't do experiments in this course. And actually, if you do experiments, chances are that things are going to go wrong in another point. Okay? No, we don't compare with experiments.
Convergence?
No, that value that you obtain, that estimate, is going to be used for convergence. But still, the question is, well, how do we know if it's a good estimate or not? Well, to start with, when I use that estimate to do error, to do convergence, I can actually see whether I obtain what we call optimal convergence rates, right? And if I do that, well, I can say that that estimate, at least for the meshes that I used, is good enough. Or you can always keep refining and use the last three discretizations to keep computing estimates, right? And eventually you will see that that estimate is not going to change much. And then you can say you converge to an estimate of the exact strain energy. Okay? Yeah, so, yeah.
But I don't see how this then, that only tells you something about how well it performs, right? Not exactly on if it's good or not. Yeah, like, for example, if it doesn't change, but it's still really bad. Then
No, but you would expect, as you refine the mesh, that you are going to get better estimates.
yeah, okay.
So say your first estimate you obtain, because these three meshes are normally what we do is we use different levels of discretizations, right? So let's say, for the sake of the argument, like I used very coarse meshes in the beginning, very coarse meshes, right? Well, I'm going to estimate, and that estimate value is not going to be very sharp. But as I keep refining the meshes and my solutions get increasingly more accurate, you would expect that that estimate gets closer to the actual value of the strain energy.
Okay.
Yeah?
Yeah.
All right, let's continue. So, as I said, when we do this, we accept an error. We accept an error. By the way, not always there is going to be an error, right? If it just happens that the problem is simple enough that I can find the exact solution in that subspace, I still have the exact solution, and therefore there is no error, right? And that actually happens a lot, many times. In fact, normally when we try a new finite element formulation and we see, we verify our implementation, normally we solve problems for which we know the exact solution. So for instance, if I try, let's say, a quartic polynomial formulation, right? Well, for instance, I would actually solve for a quartic for a problem for which I can find the exact solution as a quartic polynomial. And then if I get zero error, then I can say, well, my implementation is verified. And you're going to actually do this in the project. So when you are modifying this finite element code that I will give you, right, in the P version of FEM, you are going to go higher in polynomial order. And one of the steps to get your implementation verified is, well, you're going to find a way to make sure that the implementation is correct. And you do that by solving simple problems for which you know the exact solution is a polynomial of certain order, and you get zero error. That is the way it works, okay? Okay, so then now that we accept that there may be an error, how do we write the finite dimensional form, right? Or in this case, it's going to be our Galerkin projection. So now we find UH, again H, superscript H denotes that we're already working in a finite dimensional space, and of course that is going to belong to this subspace EH, such that, well, again, the bilinear form is equal to the linear form for all functions WH in that finite dimensional space EH of omega. Yeah? And as I think I said this, yeah, I said this a few minutes ago, if U and W are chosen from the same finite dimensional space, that leads to what we call a Bubnov-Galerkin discretization, right? And if they are chosen from different spaces, and there are reasons to do so, right, it's called a Petrov-Galerkin discretization, right? And for instance, people in fluid dynamics, finite elements are actually bad for convection dominated problems, and therefore the Bubnov-Galerkin approximation has issues, right? You can have oscillations in your solution, and therefore the way they actually solve for this problem is by choosing what the so-called Petrov-Galerkin approximation, where you chose functions U and weight functions W from different spaces, right? And in this way, you can actually solve for convection dominated problems with finite elements, and that was the main let's say, innovation by the so-called SUPG, or streamline upwind Petrov-Galerkin, again, Petrov-Galerkin there in the name, formulation that was introduced to solve flow problems. Okay, so if UH, WH belong to EH, to the same space, then that leads to the so-called Bubnov-Galerkin, otherwise Petrov-Galerkin. Okay, and now we are going to see a very important concept of the Galerkin approximation, and this is what makes this so beautiful. And the fact is that the error is nowhere. I'll show you in a minute how this works. So this is the orthogonality of the error. Okay, so say you start our initial infinite dimensional space, right? If you remember, we call it, we said, well, find U such that B of U and W is equal to the linear form for all W that belongs to the infinite dimensional space. Yeah. Now, since this is valid for all W in that infinite dimensional space, it is certainly valid for that EH, for a subspace. Okay, so I can write B of U, comma, omega H is equal to this for all WH belonging to this subspace. And I'm going to say this again. Because of the first equation is valid for all w's in an infinite dimensional space, right? It is certainly valid for a subset of w's or a subspace EH. Okay? Well, and this is because, of course, this is a subset of that. Well, if I take the second equation and I subtract then you get, sorry, this is UH here, comma, and what you see here, what I wrote here, what is it? U minus UH.
error.
It's basically the difference between the exact solution and my approximation. That is the error, right? And what this last equation says, you can interpret it in many different ways. But essentially, what this says is that in the sense of the bilinear form, right, the error is orthogonal to that space where you are projecting your solution. Yeah.
Why do we have on the right side we have 0 and on the left side we still have WH? Shouldn't it be WH minus W or W minus WH? So when you do subtraction in the B you get U minus UH and WH, right?
Yeah, because I am missing something here. I am missing a term. Sorry, I'm missing an equation. Because I am missing one equation that is basically before this. That's why I'm going to write this. Give me a second. Because it's like this. This is what I'm subtracting. So I basically take this equation and I subtract that equation. That is why on the right hand side you have equal to 0. Yeah. So what we have found here is that there is this really nice property of the error that says that in the sense of the bilinear form, your error is orthogonal. So you can think of this bilinear form as being some sort of dot product, right? If you remember, when the dot product is equal to 0, then two vectors are orthogonal in Euclidean space. Well, something very similar happens here with functions, right? So what I'm saying here in this equation is that this guy here, which is the error, right? If I do the dot product, right, with WH, and that is equal to 0, this error is basically orthogonal to that WH. And remember, I'm talking about all WHs in that finite dimensional space. So let's try to do this with an analogy. So we're talking about some Euclidean space, and then this is a two-dimensional space, and say that our exact solution, let me see, this is our exact solution, the vector of the exact solution. So this guy here is U, and this guy here is U minus UH, and this is UH, right? So this two-dimensional space, so if you look at it, this is again an analogy, right? Function spaces are different than Euclidean spaces, so we're doing an analogy with an Euclidean space. And what I'm saying here is that our exact solution is a vector that lies in three-dimensional space, right? So what the Galerkin projection does is basically projects that vector into my subspace. In this case, it's a two-dimensional space, right? And what this basically this last equation is telling you is that the error, which is the red arrow there, is actually orthogonal to that space. Okay. So again, it's this analogy. So basically, this U, my U belongs to R cubed, right? And then this EH of omega is basically a plane, right? Yeah. Again, an analogy. So how you can interpret this last equation? Well, three ways of saying the same thing. The error U minus UH is orthogonal to the subspace, but again in the sense of the bilinear form. Another way to say the same thing is that UH is the projection of U into that subspace, and that's why many people call this the Galerkin projection. So you probably heard, maybe at that point, people in dynamics use this Galerkin term a lot, Galerkin projection. And another way to say the same thing is that from all functions WH, basically that UH is the one that minimizes the error. Yeah? And again, you can see that by doing this Euclidean space analogy, because of course the closest point in that plane is going to be a straight line, right? A straight vector from that U vector to that plane. So that UH is the one that really minimizes the error. And all of these are basically equivalent statements. So this is great. So we found a way, right, to find. So if we choose functions from a finite dimensional space, and we do a Galerkin projection, we can get this satisfied, that we can find what is the best function in that space that minimizes the error with respect to the exact solution. This is incredible, right? Because we have a lot of functions in that subspace. Remember, a subspace, if you think about, for instance, let's just think about the simplest case. You have linear polynomials, right? And I assign, you can represent that space as being basically the sum of basis functions that are linear multiplied by these coefficients, right? How many functions we have? How many U we have? If I take only linear polynomials as my subset, how many functions we have? Infinite. So from my subspace that is composed only by linear polynomials, I still have an infinite number of functions that I can plug into that equation. But the moment I do the Galerkin projection, I pick up what is the best one of them. This is a remarkable invention. And that is the basis of everything we do today in approximation of partial differential equations, right? The basis of the Rayleigh-Ritz method is exactly this, the Galerkin projection. It's just that in that case, our functions have global support. Yeah, what was fantastic about the finite element method is that, well, you decompose your big problem and then into small subdomains, and you say, well, each subdomain is going to have very simple localized behavior, right? But this still holds, so you are finding the best approximation within that space of functions. So we are doing pretty well so far, even if we choose linear polynomials. And that is why these methods work so well. I mean, everything we do for solving boundary value problems is now today based on these ideas. I'm talking about solid mechanics, okay? Fluid dynamics is a bit different because they use other methods. Yeah? I want to finish here this class because then we are going to start looking at the finite element formulation, right? So far, again, this is not finite element method because this is still the Galerkin projection. The finite element method, you can say it's a subclass of this Galerkin projection, right? But there are other approaches. You can choose Fourier series that span the whole domain, right, as your approximation space, and then get a good result. So I will finish here. Do we have any questions?
Yeah, well, in the subtraction that you have,
Yeah.
could you go to that part? So when you subtract BU WH, and then you subtract BUH WH,
Yeah.
on one side you have U minus UH when you in that final answer.
Yeah.
And then you also still have WH. What I would expect is WH minus WH equal to 0.
No, no, because well, if you plug this into the actual bilinear form, what you get is what you have here, right? Yeah, you can check, but this is the, because these two are different. But remember that this is a bilinear form, so this WH is still going to be the same in both expressions. So you can factor that. So you're going to have this term popping up.
Yeah, but I don't see how.
Now on the right hand side is different, right? Because you do have the same term, and therefore you subtract to 0.
Yeah.
But on the left term, because these two things are different, so U is the exact solution and UH is not, then you're going to get this. Yeah?
So if on top you would have W and U, would you get W minus WH as well?
Sorry?
So if on the top term in the subtraction, you would have UW, would your answer be U minus WH and W minus WH?
In that case, it would be more complicated, huh? And I think it's not going to be, yeah, so you could apply some of the properties that we saw, but I would say that it's not going to be as simple as just U minus UH. It's not going to be one expression. I think you can actually lead to more terms, and it's not going to be as simple as this. Okay, so we stop here. Please keep looking at the nota bene, right? All the material that we're covering in these courses is also in the book chapter, and I will start also replying to some of your questions in the nota bene as well if I don't see that anybody is replying. Yeah, no more questions? All right, thank you guys.